Tyranny is a human trait that we sometimes project onto nature. This projection is a form of rationalization, perhaps a means to cope with matters that we cannot control. Such is the case when we invent machines to free us from the bounds of Earth, affecting our escape into space. If we want to expand into the solar system, this tyranny must somehow be disposed. Rockets are fundamentally momentum machines. They spew out a hot gas out of a nozzle at a high velocity, causing the nozzle and the rocket attached to it to move in the opposite direction. Isaac Newton correctly defined the mathematics for this exchange of momentum in 1687. Conservation of momentum applied to a rocket was first done by a Russian visionary and scientist Konstantin Tsiolkovsky in 1903. All of our rockets are governed by Tsiolkovsky's rocket equation. The rocket equation contains three variables. Given any two of these, the third becomes cast into stone. Hope, wishing, or tantrums cannot alter this result, and although a momentum balance, these variables can be cast as energies. They are the energy expenditure against gravity, often called delta V, or the change in rocket velocity, the energy available in your rocket propellant, often called exhaust velocity or specific impulse, and the propellant mass fraction, how much propellant you need compared to the total rocket mass. Failing to follow these equations will cause your rocket to break the laws of physics. And that is exactly what we are going to be doing today. Hello everyone, my name is Deltlead, and today we're going to fly a ship capable of traveling faster than the speed of light. This spaceship is available for download at the SimpleRockets website, and it is unmodded, so all my fellow mobile players can enjoy flying it as well. Now, obviously SimpleRockets is just a game, and with any game there are exploits and ways around the so-called laws of physics and Einstein's theory of relativity or whatever. But there are theoretical models for ships that could travel faster than the speed of light that have yet to be proven impossible, and they satisfy all of our current theories on physics and relativity. One such theoretical engine capable of propelling crafts faster than light, and the inspiration for this build, is the Alcubierre drive. Instead of expelling mass to change the momentum of your rocket, the Alcubierre drive creates a sort of warp bubble around your ship. This bubble of warped space-time moves forward in the direction of the ship, while the ship itself sits motionless relative to the bubble. The ship experiences no acceleration, and there are no relativistic effects like time and length dilation. This gets around all of Einstein's pesky theories on relativity that say it's impossible for massive objects to accelerate past the speed of light. To be clear, the Alcubierre drive does not exist, except for on paper and some computer simulations at some high-level universities, and we have no idea how to actually build one as they require exotic matter with negative mass, to create the warp field. Nevertheless, technically the Alcubierre drive is possible, and technically possible is the best kind of possible. This is the ISP Damocles, an interstellar warp ship powered by the most advanced technology the Druids have developed so far, and today we're taking it on a tour of the Juno system. Our first destination in this tour will be Tydos, the gas giant that's second farthest away from the Juno system, and the largest planet in the Juno system with several very interesting moons to explore. We're going to be putting a lander down on each of these moons to establish our presence in the Druid system. The Damocles has two engine modes, a high warp factor mode and a low warp factor mode. The high warp factor moves the Damocles at impossibly fast rates and can accelerate up to the speed of light in mere minutes. The low warp factor mode can move the Damocles at more typical speeds, accelerating faster than any conventional rocket engine, but it would take years to accelerate to the speed of light. So we will use the high warp factor mode to break from lunar orbit and set out on our trajectory towards Tydos. Then, as we approach, we will use the low warp factor engine to adjust our approach and put ourselves in a specific orbit around Tydos. Now that we're orbiting Tydos, let's target Nebra. Nebra is a volcanic moon with a vast ammonia ocean and a thick, toxic atmosphere. Silicate volcanoes have formed chains of islands across its surface, but the dense atmosphere makes landing on them a real challenge. Luckily, our landing pods have corrosion-resistant coatings that will maintain their integrity in the extremely caustic conditions, even if we miss the islands and land somewhere in the ocean. Now that we're in a stable orbit of Nebra, we'll power down our Alcubierre drive and prepare to deploy our first lander. These landers are equipped with open expander cycle Methalox engines, life support systems, and communication equipment. They're sufficient for establishing a standalone outpost on a planet's surface. A short retrograde burn will put us in a suborbital trajectory into Nebra's atmosphere. We'll then rely on our heat shielding and the parachutes equipped on this lander to slow us down into a nice and stable landing on the surface. And with that, we've successfully splashed down in Nebra's ocean. Our capsule has plenty of buoyancy on this low-gravity moon, and with the density of the ammonia oceans, we are in no danger of capsizing or sinking. Now, with our first moon explored, let's shift our attention to our next destination, Miros. Miros is a rocky and barren moon with an extremely low gravity and a very low orbital velocity of only a few hundred meters per second. We'll engage our Alcubierre drive and jet away from Nebra towards our next target. There is no atmosphere around Miros, so we will need to use our landing engines for the entire descent. We'll undock our lander and let it float away from the Damocles before pointing at retrograde of its orbital velocity vector and firing its engines for the initial descent burn. These landers use no tinkered or XML edited parts, and are also available on the SimpleRockets website if you would like to download them and try them out yourself. A stock version of these landers and the ISP Damocles are also available for any mobile players who would like to try them out. Even when landing on sloped hills or uneven terrain, the suspension on these landers is more than sufficient in stabilizing it and keeping it from bouncing off the ground. If you're designing your own landers, I highly recommend you build custom landing gear using pistons and springs instead of trying to use the stock landing gear the game provides. The stock landing gear tends to be bouncy and often slides across the surface without getting proper traction, which feels very unrealistic and makes landing on planets extremely difficult sometimes. With our lander successfully touched down on Miros and showing green across the board, it's time to move on to our last destination around Tydos, the ice moon Orcus. Orcus, like Miros, is devoid of an atmosphere. It has gravity weaker than Nebra's, but stronger than Miros's. It's mostly inhospitable, and with no geological activity or strong tidal forces from a closer orbit with Tydos acting upon it, it's extremely cold. We'll put our last two landers down on Orcus to make a larger outpost here at the edge of the Tydos system. With our first lander down, we'll try to place our second lander as close as possible to the first one. This can be a bit tricky sometimes, but with practice I can usually get my landers within a kilometer of each other. This time I got pretty lucky and landed within 500 meters of the first lander. After a few tactical bunny hops, we managed to inch our two landers very close together to form a nice tight outpost here on the surface of Orcus. Now that all of our landers are deployed on the moons of Tydos, it's time to complete our mission. The ISP Damocles will do a flyby of Urados and its moon Taurus before accelerating out of the Juno system and towards the unexplored outer reaches of our galaxy. We'll target Urados and spool up our Alcubierre drives one last time as we tear off towards the very edge of the Juno system. And with that, we have cleared the last planet in the Juno system and are off, accelerating up and past the speed of light in our spaceship, and as you can see here, even video games don't like it when you break the rules of physics. But we're off to boldly go where no Drew has gone before. One day the Damocles will return to the Juno system with its treasure trove of knowledge and data, but for now it flies into the inky void to discover what lies beyond. Thank you guys so much for watching till the end of the video. I really appreciate the support. You guys are the reason I love making SimpleRockets 2 videos, and I hope you enjoyed this one. Now, as I promised at the beginning of the video, the secret to making this ship is an XML-edited ion engine. I set the fuel and power consumption to 0 and the thrust to around 10 billion times that of a normal ion engine. It's not hard to do, it's about one line of text that you add, and if you want to see exactly how I did it, you can download the craft with the link in the description and open it up for yourself. Thanks again for watching, and I'll see you in the next mission.